So welcome everybody. Welcome to the Stanford Data Science for Social Good final presentations for the summer 2022. We have two teams that have worked on projects with partners over the last 8 weeks, and I'm going to present their work today. One project is on COVID mortality, and the other one is on data journalism. The COVID mortality team will go first, followed by the big local data journalism team. Each team will speak for 20 to 25 minutes, followed by 5 minutes for questions. Then at the end, the teams will all stay on for further questions. As you hear these presentations, feel also free to add items to the Q&A at the bottom of your Zoom. So welcome to the presentations, and maybe the COVID mortality team, please start.
Thanks, Naras. Okay, can you all see our slides okay? Awesome. Good morning, everyone, and thank you for joining us at the Stanford Data Science for Social Good final presentations for summer 2022. I'm excited to start us off this morning with our project, Determinants of U.S. County COVID-19 Mortality. If you don't mind going to the next slide, Kevin, thanks. My name is Scout Leonard, and I'm joined this morning by my teammates, Jianchen Ge and Charles Hendrickson, and we had awesome leadership this summer from our DSSG mentor, Min Sun, who's also on this call today. So I'm going to get us started with some background and some of the significance for public health that motivates our project and give us a quick overview. And so since the start of the pandemic, more than 1 million Americans have died of COVID-19. COVID-19 has contributed to increased mortality in the US, but it's hard to know how much of that mortality has been accounted for. Attributing cause of death to COVID-19 has been and it remains a challenge. Hurdles to correctly quantifying COVID-19 mortality burdens include challenges to declaring COVID-19 as cause of death, like lack of testing and testing sources. And there are also hurdles to correctly quantifying COVID-19 mortality burden that are from indirect causes of COVID-19. These include interruptions to the healthcare system and the more broad socioeconomic circumstances of a global pandemic. And so for these reasons, estimating excess death can be a more effective way to understand the mortality burden of the COVID-19 pandemic. So while there's this challenge of understanding the true mortality costs of the pandemic, we try our best to understand this mortality burden with metrics such as excess death. And we're going to talk a little bit more about what exactly excess death means on this next slide. But trying to understand it this way is really important because the closer we get to understanding the true mortality burden of COVID-19, the more accurate data we have for informing effective public health policies. So our analysis in particular estimates this excess death value, and it does so at the US county level. And this is an important spatial scale because US counties are a more heterogeneous unit when compared to states or the country as a whole. And by estimating excess death at the US county level, we have a tool to better understand the socio-demographic features that influence COVID-19 mortality. These excess death estimates at the county level can be used to study the most important determinants of COVID mortality, including economic features, public health measures, health and well-being factors. And for counties, this is really essential information for their power in creating effective interventions and helping communities to take protective actions for future public health crises. And so before I talk about some of the main goals of the project, I just want to clarify some terms so it's not too jargony for us. So one of the terms that we'll be using throughout this presentation is all-cause mortality. And all-cause mortality is just the measured total death in a time period regardless of cause. We can often get this value from death certificates. The second term that we'll be using quite a bit in this presentation is expected mortality. And expected mortality is a predicted number of all-cause death based on historic measured data. So we can use all-cause mortality from years prior to the pandemic to predict the the expected mortality for 2020 and 2021, assuming there was no COVID-19. And finally, we'll be using the term excess mortality quite a bit in this presentation. And this is just the difference between the measured amount of death, all-cause mortality, and the expected amount of death, expected mortality. And this gives us the number of deaths in a particular time period relative to normal times in the case of the pandemic. And so with this motivation for calculating excess mortality and some of these terms out of the way, the main goals of this project were to fit a model to predict expected death and calculate excess death using that expected death value at the US county level. And we did this for the 500 most populous counties in the US. And second, we wanted to use these values to determine static and policy values that contributed to the excess death rates for 2020 and 2021. And so on the next slide, we have a figure that shows how we did this. At the top, you can see sort of phase one, where we achieved the first goal of predicting expected mortality rates using historic data from the CDC to fit our model and predict expected mortality for 2020 and 2021 and calculate the amount of excess death for those years. And then we pull in all of these features, intrinsic, vaccination, and policy features for all of the counties included in our models. And we fit 4 different models and compare their prediction accuracies and use those to determine important factors in COVID-19 mortality. So next, I'll pass it off to Charles, who's going to talk about that phase one, first part of our project.
Thank you, Scout. For phase one of our project, we utilize all-cause mortality data from the CDC Wonder online database, which hosts the National Center for Health Statistics mortality data. This data has national coverage for all US counties and comes in 2 forms. Final annual all-cause mortality data, which is available from 1999 to 2020, and provisional data, which is available from 2021 to the present. We use all-cause mortality data from 2008 to 2022 for the top 500 most populous counties. Based on historical trends in county level all-cause mortality data from CDC Wonder, we can predict the number of deaths that would have occurred in each county for 2020 and 2021 had the COVID-19 pandemic not occurred. And this is known as expected mortality. And we make these predictions using the following fitted model. We used a regularized Poisson model, which is outlined in green, to predict county level expected mortality for 2020 and 2021. And we chose this model because it is best used to model count data such as all-cause mortality. And we tried using a quasi-Poisson model to account for overdispersion of the variance. However, the regularized Poisson model that we use ultimately had a lower root mean squared error. In this model, there's a lasso penalty, L1, and the ridge penalty, L2. We add these penalties for regularization to avoid overfitting our model. T is time, and death T is the all-cause mortality at time T. Pop T is the normalized population at time T. And beta 2 is the coefficient for each of the 500 counties. Beta 3 is the interaction term between each county and time. We trained the model on 2011 through 2018 all-cause mortality data, and we validated the model on 2019 all-cause mortality data. With our final fitted model, we generated expected mortality estimates for 2020 and 2021. And when comparing our model's predictions for expected all-cause mortality to actual all-cause mortality, they differ as expected for a normal year like 2019 and for abnormal years like 2020 and 2021. And we visualize these predictions here. So in the scatter plots shown here, points found on the solid 45-degree line represent counties where we predict no excess deaths occurred. Points found above the line represent counties where we predict excess deaths occurred. And as you can see for 2019, we see that most points are found on or very close to this line. And this result supports our expectation that we shouldn't see excess deaths in 2019 because it was a normal year. However, on the right, for 2020, we see that almost all the points are above the line. And this result makes sense because we expect to see increased excess death in 2020 due to the pandemic. Similarly, for 2021, we see that there's almost all the points are above the line. And this result also makes sense because we expect to see increase in excess deaths continue from 2020 to 2021. Additionally, we visualize these patterns on a map of the United States, which shows estimated excess death crude rate for the top 500 most populous counties. And counties that are not included in the top 500 most populous are shown in gray. Compared to 2019, we see a large increase in excess death crude rate in 2020 for most of the top 500 most populous counties. Similarly, in 2021, we see an increased excess death crude rate for most of these top 500 most populous counties. And now Kevin will present phase 2 of our project.
Thank you, Charles. Thank you, Scout. In phase 2, we are studying the features related to the excess deaths, and we consider data from 3 categories. First, intrinsic socioeconomics and health features. All the features are numerical values, and the income ratio here is income ratio between the 80th quartile household income versus the 20th quartile household income. The bigger income ratio, the bigger discrepancy in the high income and low income group. There are in total 7 intrinsic features. The second category is the policy features. There are also 7 policy orders. And for each order, we calculate the number of days between the order start date and the 2020 January 20th, which was the date of first COVID cases identified in US. And we use this number of days to measure how soon did the government respond to the pandemic. If the county did not have a listed feature, then we use the state level order start date as a substitution. But it also could be that the state has also never imposed such a restriction. So we convert all the number of response date to the ranks and gives the counties with NA start date the biggest rank. For the shelter in place order specifically, we also include its duration and gives the rank. The third category is the vaccination data. We consider the percentage of population received first dose and also complete series of doses. Because it's possible that during a time period, a county has a bump in its number of vaccinated population. So we calculate the area under a curve for a fair comparison between counties, their number of administered doses. And here are some preliminary data visualizations of our intrinsic features. The high excess death represents the counties with the highest 10% excess death rate, and vice versa for the low excess death group. And we can see that intuitively, the high excess death rate is positively related to a percentage of adults with diabetes, overcrowding, income ratio, and negatively correlated to primary care physicians rate. And the outcome excess death is also negatively correlated to the vaccine administration. For the policy features, we note that for a county, most cases they announce the restrictions at the same day. So many start data will be the same. That's why we did a principal component analysis for the restrictions. The PC1 points roughly to the direction of outdoor rec, non-essential business, food and drink, and entertainment. PC2 roughly points to shelter in place, its start date, and also its length. Mask requirement is in between PC1 and PC2. We only keep the first two principles for further modeling. And in the first round model selection, we compare our validation RMSE on 100 holdout test counties, and we compared the RMC for the 4 models: linear regression, lossy regression, random forest, and XGBoost. RMSE is mean square root of mean square error, and the smaller the better. For all models, we average the dependent variable excess death rate across the 2 years. And for the intrinsic features, we also average them, and we add up the 2 years vaccine area on the curve. And for the policy principal components, they are the same for 2 years. And in the first round model selections, we include all the features. We can see for the regression models, the lasso regression wins out because of the lower validation RMSE. For the tree-based model, XGBoost wins out. So we choose to keep the right 2 models for future comparison. We know that in our features, there are a lot of multi-collinearity issues. So for example, the percentage adults with diabetes is highly correlated with percentage adults with obesities. And the administered dose 1 population percentage is highly correlated with serious complete population percentage. So we decided to remove some of the variables. We removed the obesity, uninsured, housing burden, and a population with complete series of doses. And we keep 7 features. 4 of them are intrinsic variables: percentage adults with diabetes, overcrowding, income ratio, primary care physicians rate, and 2 policy principal components, and 1 vaccination data. Those 1 population percentage error curve. After the feature selection, the RMC end up with lower value for the lasso regression and actually higher for the tree-based XGBoost. But it's not too bad for the prediction. But on the other side, removing some of the correlated features can help us better understand the contributions of the features. So we decide to use the models with fewer features. And we measure the contribution of the features by the permutation feature importance score. We first compute the negative RMSE of the 2 models. And for each feature, we randomly shuffle the data in the column J to generate a permuted version of the data. And we computed the negative RMSE again on the shuffle data. And the feature importance is defined as the decrements in the negative RMSE. And we do this for 10 times for each feature. And we average the permutation feature box score and normalize them. Here are the 2 permutation feature importance bar plot. According to both models, regression and tree-based models, percentage adults with diabetes and income ratio are the top two most important features. The higher percentage adults with diabetes, the higher income ratio, the higher excess deaths. And we will also understand the effect of the vaccine and policy features by example. We use the Taylor County from Texas and San Francisco County from California to understand the adding new variable effect. We will first see the prediction with only intrinsic features, then we add up policy features and vaccine features. And the excess death rate is the crude rate, so we already adjust according to their population. And the prediction is made on a held out test validation set. With only intrinsic features, the prediction number for San Francisco is 124 and 109 for Taylor. After adding policy features, the predictions become 118 and 122. After adding the vaccination feature, the prediction become 108 and 145 respectively. And we are comparing them to the phase 1 excess death rate. And we can see that the prediction is getting closer to the phase 1 excess death rate. However, not every county follows this pattern. Some of them actually deviate from the phase 1's number. As we can see here, the interval is the confidence interval. It's pretty wide. So we admit there are still a certain amount of uncertainty in our prediction. So this might be something we can do in the future to get a better prediction. And interesting, we see that, okay, I can show it once more. The prediction for San Francisco keep going down. In contrast, the prediction number for Taylor County increases. And let's take a look what's different about these two counties. As we can see here, the vaccination rate in San Francisco is much higher than Taylor County. And there are a higher percentage of adults with diabetes in Taylor counties, and fewer adults have primary care physicians rate in Taylor. For the COVID restrictions, California imposed a shelter-in-place order in March 19th, and it lasted for 312 days, while Texas issued a shelter-in-place order later than San Francisco and California, and it only lasted for 30 days. And 8 weeks have flown by. If we had more time, we could add interaction terms and partial dependence plot for the regression models. And there are still a lot of work ahead in quantifying the magnitude of importance of our features. And also, we only study the correlation, but we are also interested in studying the causal effect of all the features. And we wish we could access the data that gives policy compliance level. This can help us have a better prediction, also improve us understand the effect of policy orders. Also, policy and vaccination features are time dependent. We can wait a bit longer and see if there are long-term effects. Also, there are quite limited granular data for the county level, so we can compare our result with state level and country level analysis. We really appreciate all the help and support from our mentors, faculty mentors, and DSSG cohorts. Thank you so much for the great summer. Thank you. Does anyone have any question for our group?
There are 3 questions in the chat, so I'll read them out to you. So
Okay.
first question from Rob Tifshani is, why was the percent obesity removed?
Because we know that obesity is highly correlated with diabetes, and we just stick to diabetes population percentage. I tried using both, but there's no significant difference in the RMSE and also the feature importance.
And also the 2 other questions, how did you compute the prediction intervals and how would you assess causal effects?
For the interval, actually, I only did the confidence interval due to the time limit. I could you do the prediction interval in our future work, and for the confidence interval, it's just the mean plus the how should I say, that's the standard deviation times the coefficient.
And I can address the question about causal effects. I think this is something we've not necessarily thought too much about, but we've talked a little bit to Mia, one of the technical mentors, about, and she said it would be interesting to take one state as a case study and look at a causal effect. So just California, but we're not quite there yet. And
yeah, we probably need to do some propensity score matching and compare the counties we find interesting.
Thank you.
Did I answer all the questions?
Those
We
are all
can
the
also
questions in
give
the
a
chat.
chance. Sorry about that, Scout.
Oh, no,
we can also give a chance to Charles maybe to add to that. I saw Charles, you unmuted yourself for a second there.
I think Scout nailed it with addressing that last question, but we see there's a lot of potential to do future work on this project, and taking a stab at some of these future directions is definitely where we'd like to head.
Are there any further questions? If not, let's thank the speakers, and they'll stay around for their after this thing too. Thank you.
Thank you.
Our next project group is the Big Local Data Journalism Group, and please take it away.
Hey everyone, good morning or good afternoon, depending on where you might be. My name is Alex. I'm part of Team Big Local, and we're here today to present our project identifying behavioral health conditions in police encounters as part of the Stanford Data Science for Social Good Fellowship in collaboration with the Big Local News Organization and California Reporting Project. And so first, I want to introduce the team. We have the student fellows, which is Amanda, Grishma, Salil, and myself. And then we also have our technical mentor, Chan, our faculty advisor, Naras, and Lisa Pickoff-White, who's our community partner and a data journalist. And so when we start, I'm going to pass it off to Salil, who's going to go a bit into the project background.
Thanks, Alex. So the prelude to our story started in 2018 when the California State Legislature passed a bill that made police records relating to officer use of force incidents publicly accessible. And what journalists did after this bill was passed was, well, access these records and dig through them. And what they found was that in the 4 years before COVID, over 3,500 people were seriously injured or killed by law enforcement. Now, these journalists had a suspicion that behavioral and mental health conditions could have been a factor in a lot of these cases. And of course, this is important because officers are supposed to de-escalate situations that involve behavioral and mental health conditions, because people that have behavioral or mental health issues don't respond to commands in the same ways. And what they ended up finding when they dug through the reports was that police departments often vastly underreport the proportion of cases in which they use force, but that also involve behavioral and mental health conditions. And for Bakersfield in particular, the police department reported that number, or their estimate of that number was off by a factor of almost 18 from what the journalists estimated by digging through the reports. And now the way the journalists did this digging through the reports was that they would request the documents from the police departments as large PDF files. They would upload them to this website called Document Cloud. And then they would assign 3 people to look at every single case. And this serves as sort of a peer review process to mitigate human error. And the thing with this is that, by having 2 readers read through every case and the reviewer make sure or validate what their readers found, is that analyzing every case ends up taking them on average 3.5 hours. And what the reviewers are doing as they're going through the documents are digitally annotating any place in the document they see that might indicate a behavioral or mental health condition. And now I'll give it to Amanda to sort of give you a sense of the scale at which these journalists are working.
Thanks, Leo. So we know that the case review process takes 3.5 hours for every case that they go through, but it's really the scale of the data that creates a need for automation. So far, journalists have gone through all the cases for 6 agencies, and that's taken them the better part of a year. But there are still 464 agencies that are yet to be reviewed. And so essentially the bottleneck here is that 2 journalists have to review every single document in a case, even though the large majority of the documents are actually not relevant to what they're looking for. That's why our goal is to build an automated classification pipeline that can detect whether each document contains mention of behavioral health conditions. So here are just 2 examples. The top is a narrative and the bottom is a form that we would want to classify as true. The top contains mention of cocaine and BAC levels of 0.07%. And then the bottom also references that the subject was under the influence of drugs and or alcohol. So that's why we want to classify each of these as true. Ultimately, after we build our automated pipeline, we find really good results. Essentially, now journalists only have to review documents that are flagged as positive, which is about 15% of the total documents. And this reduces the total time it takes to review a case from about 3.5 hours to now just 45 minutes per case. And so we estimate this to be 75% reduction in how much time it would take the journalist to review a case after automation. Now I'll just give kind of a brief overview of what our data looks like, because our data actually sits at sort of 4 different levels. At the highest level, there's the agency, which you can think of as like a police department. So we have data from 3 agencies, and then within those agencies, there are many cases that belong to that one agency. And so we have 350 cases that span the 3 agencies that we have data from. And then for any given case, there's many documents, and each document consists of several hundred pages sometimes. And the reason that these documents are so long is because oftentimes what agencies will do is they'll append together many different files that are actually distinct into one long PDF. And so this is something that we're going to have to actually think about further in our pipeline. But just recall that we want to classify things at the document level. And then just to give a high-level overview of what our pipeline is, this is exactly how our community partners at Big Local and CRP will be using our work. So essentially what happens is they're going to select a county that they want to review and analyze the cases for, and we'll connect to the Google Drive path where all the PDFs and the files for that given county sit. And then for each document within that county, we're going to split it into distinct pages, so that pages that look more like forms will go into the forms pipeline, and pages that look more like narratives will go into the narratives pipeline. And the reason 2 pipelines are necessary is because the forms and narratives pages have very different structures. So we use different tools that can optimize these structures to improve the accuracy of the classification for that page. In the end, we're going to get a final classification for each document by aggregating the label from the forms pipeline with the label from the narratives pipeline. And so double clicking into the page type classification, recall essentially that a document can have a lot of different files appended together, and we need to separate forms from narrative pages. And so thanks to Helena at UC Berkeley, she built a page type classifier that we were able to use that in the end gives us the document name, the page number in the document, and the path to that page image, as well as the page label. From here, the form pages will be given to the forms pipeline, where we'll then use a Azure form recognizer to analyze the structure of the form. The goal here is to really identify which forms actually mention behavioral health conditions, and then if they do mention behavioral health conditions, explain why. So when we analyze a given page, essentially what happens is we'll analyze all of the checkboxes using a Azure form recognizer and select the ones that are A, selected, and then B, relevant. And we determine relevance by whether or not there's some sort of mention of behavioral health conditions words, such as intoxication or influence. Once we have a label, so if there are relevant checkboxes that have been detected and are selected, then the label is true and will output the relevant information, such as what text our partners can scan for and which page it might be on in the document. However, if the label is false, we have to take some additional steps. Essentially, what we do is we rescan the page and output any narrative text. And when I say narrative text, what I'm really talking about is if there's any paragraphs that the officer may have written as a description of the case or to summarize the case. And the reason for this is twofold. First is because sometimes on a given form, which we'll see in the next page, you'll have a section for checkboxes and fields that the police officer can fill in. But then at the bottom, there will also be an option for the police officer to type up what he remembers from the incident. That's the first reason. The second reason is sometimes the page type classification will actually accidentally classify narrative pages as form pages. And in both of these scenarios, Azure Form Recognizer isn't really processing or thinking or analyzing the narrative text. And so we need to do some further analysis to actually determine whether or not the form has mention of behavioral health conditions. And so ultimately, this will be fed into the narratives pipeline to be analyzed further. And here are just some examples of the outputs from forms. So on the left-hand side is a positive label because we see that there's a checkbox that references drugs and alcohol influence. And so the output will be true with the text that the journalists can scan for when they're going back through this document, and then the location. And then on the right side is a negative label. This is an example of what I was talking about earlier, where the top it contains information about forms that the officer can fill in, but the bottom, he starts to write about the incident that we need to analyze. And now I'll pass it off to Alex to talk a little bit more about our narratives pipeline.
Yeah, thanks, Amanda. So for our narratives pipeline, it's a little tricky because we're dealing with language data, so just pure text. And so as a result, we need a model that can sort of go from the whole text of the document, read it, understand it, and then be able to output whether or not it contains mention of behavioral health. The issue is that language is tricky. And so when we tried pretty naive models like logistic regression, naive Bayes, they were sort of unable to capture the data complexity, and they returned 100% negative predictions. And for an example of why this is the case, the sentence below is, when asked if the subject used meth, they replied that they had been using it all their life. And so the tricky thing with this is if you look at it one word at a time, right, it's sort of hard to encode the meaning directly like that. You know, language is recursive. It can sort of be encoded across paragraphs, pages, even sentences. And so these models are unable to sort of grab that kind of meaning that can exist in sentences like that. And also keyword search doesn't always work great. An example is if you took that sentence and said, when asked if the subject used meth, they replied that they would never use it. That would also be able to learn the meaning from that because of that negation at the very end. But luckily, in the last 10 years, there's been huge advances in natural language processing. And these have sort of championed the use of these deep neural models, which are really, really good at a variety of tasks. And so some of these include question answering, summarization of text, translation even, and luckily for us, text classification. And so the general way that one of these works is you take a pre-processed text and you turn it into a series of numbers at a certain number of dimensions called the word embeddings. You put it into your fine-tuned model and it outputs a label. And basically the accuracy of the label when you try and train the model sort of back propagates into the model, and you can adjust like that and learn like that. And so basically in 2017, Google released a new model architecture that became sort of the model of choice, the standard for a lot of these NLP tasks, and they called it the transformer. And so one of the things that the transformer does is it can process sequences of text at a time rather than just words or groups of words. And its real power comes from its self-attention mechanism. And basically what that does is it can weight different parts of a sentence that you feed it in differently. And so it can sort of understand what context is important relative to a given word or sequence of words. And they're really good at language. because they're pre-trained on billions of texts. And so they trained it on, data from the web and Wikipedia. And from there, they can be sort of fine-tuned for a lot of different downstream tasks. And so for the choice of our specific model, we chose Distilbert, which is released by Hugging Face in 2020. One of the reasons we chose it, you can see on this graph on the left, this shows sort of different models that have come out as the years have gone by, and the y-axis is the number of parameters in terms of millions. And so, the larger model, the slower it'll train and slower it'll be able to predict. The good thing about Distilbert is it's able to really mimic the performance of these a lot larger models, and the faster training and faster inference can sort of, match our need to classify these documents at scale. And so next, I'll sort of talk about what a Distilbert model pipeline kind of looks like. And so we take the full narrative text, which can be, 100,000 tokens or words. And unfortunately, due to the self-attention mechanism, Distilbert can only take in 512 tokens at a time. And so we're going to do a lot of text cleaning and a lot of text processing to sort of find out what text in a narrative is important to us. And so that we're separating a lot of all the signal from the noise. And so it takes that truncated text and it feeds it into a tokenizer. It outputs these word embeddings and this attention mask. And what the attention mask does is, let's say, this text you gave it isn't 512 words long. It'll pad it with these little tokens that say pad, and it'll just tell you what words to look at. Finally, those get fed into the model. And while we're training, you feed in the word embeddings and the attention mask, and it comes with some output probabilities. And so it's basically asking, what is the probability that this text belongs to either not mentioning behavioral health or mentioning behavioral health? And so using the loss function of the model, basically it back propagates the result of our predictions into the model. And so it always improves as we go through the data. And then finally, when you actually want to sort of know what, label we want to give it, we just pick whichever class probability is greater, and that's how we're going to predict for the text. And so next, I'll sort of give it to Grishma, who's going to go into some of the things that we did for text cleaning for our narrative pipeline.
Thank you so much, Alex. Hi, good morning, everyone. So now we know that we're going to be using Distilbert for our appropriate model, but we need data for it. So we actually get into the data side of the narrative pipelines. Like mentioned before, coming out of the page type classification pipeline, we basically have images of pages classified as forms or narratives from each document. The images of forms go through the forms pipeline that Amanda explained before. Now for the images of the narratives pages, first we use Tesseract, which is an open source optical character recognition platform to extract our raw text. After using Tesseract, we have our raw text from all of our narrative type pages in our documents. We combine these with the narratives that come out of the forms pipeline to have an overall text corpus. However, pre-processing these texts is extremely important. This is because, like Alex said, Distilbert can only process 512 tokens at a time. So we need to pre-process the raw texts as much as possible before we can feed them into our Distilbert model. So now we will be looking at the different types of pre-processing steps we adopted for our raw text. Before I get into the steps, I just wanted to quickly remark that the private details like name, contact information, etc., have been masked in our presentation for obvious reasons. That being said, so the first pre-processing step that we decided to take was masking named entities. The logic here is that since these documents are police reports that have a strict framework, they require mentioning names and details as clearly as possible. So we know that there's a lot of noise that's going to be happening there with names of people involved, names of police departments and jurisdictions, locations, etc., that we do not necessarily want. So we then decided to mask these named entities in our corpus using Spacy and named entity recognition package. What this package essentially does is it basically classifies named entities like a person's name, location, time, institution, etc. into 18 different categories. Next slide, please. So from our exploration, we found that 12 of the 18 categories that NER classifies are noise to us. So we basically mask them. However, 6 of the 18 categories like organization, cardinal, ordinal, product, percent, and quantity could have relevant information, as you can see from the bottom image. So we've decided to keep these 6 specific types in our corpus as is. Next, Salil will take us through other useful pre-processing we did before having our narrative data ready for classification.
Yeah, thanks, Grishma. So just to take stock of where we are right now, thanks to Grishma's work, we were able to take images like JPEG files of all our documents and extract the text from them and mask out names, right? But we still have a problem in that documents, as Alex had mentioned earlier, can be tens or hundreds or even thousands of pages long. And our lightweight deep learning model, Distilbert, only takes in roughly 500 words at a time. And so we want to do something smarter than just randomly truncating our text at the first 500 words. The way we do that is we first clean our text by applying some pretty standard NLP word cleaning techniques, like removing typos from the OCR, non-English characters, short words, etc. And then what we do is find where these things we call keywords appear. And we worked with psychologists at Stanford to get a list of words like drugs, alcohol, meth, behavior, influence, crazy, etc. That journalists use when they're like manually annotating documents to look for behavioral and mental health conditions. So we search the document for those words, and what we do is just extract the text in the neighborhood of those keywords for every keyword that we find. And in this way, we can get rid of a lot of the noise in the document and just keep the parts that are relevant that we want our model to learn from. And what this ends up doing is reducing the length of the document by quite a lot so that we can feed it into Distilbert easily. And I remember at this point, we're trying to train our model. This step gives us some solid input data. So this will be like our sentence embeddings of these condensed documents will be like our feature matrix, right? But we still need labels in order to actually train a model. So I'll hand it back to Grishma to talk about how we generated those labels.
Thank you so much, Salil. So now that we're going to be focusing on labels. So initially, we were given case level classification data with the labels classified for each case. However, from our exploration, we found that some documents within a case may or may not mention behavioral health conditions, but the case will still be labeled true since we have case level labels. So this basically meant that since we're doing a document level classification, we now needed to create good document level labels ourselves. So after a little bit of brainstorming, we decided to use the manual annotations that journalists highlighted within a document when they looked through it to create a document level label or ground truth. In a general sense, what this means is that if a document contains relevant annotations, we would consider it to have a positive label. Otherwise, we would consider it to have a negative label for behavioral health. But what do I actually mean by relevant annotations? We already know that there are several annotations added by journalists manually in a document. So we first use Document Cloud API to extract all of these annotations present in all of our documents. After that, we used a list to filter out the annotations that were relevant based on whether the title of the annotation had a word that belonged to this list. Our list contains words like erratic, alcohol, mental, influence, etc. Please note that this list was evaluated by our community partner, Lisa, as well as 2 Stanford psychiatrists researching behavioral health conditions. Therefore, we have reasons to believe that this list is appropriate, inclusive, and robust for our purposes. So ultimately, if our annotation title had a relevant word, that document was classified as a positive document. Otherwise, it was classified as a negative document. You can see an example of a positive versus a negative annotation on the right side of the screen. The top annotation has the word influence in the title, so it is deemed relevant for our purposes. However, the bottom annotation has no relevant keywords, so it is deemed negative for our purposes. Although we will not go into the details of how this filtering fully worked, please note that we've tried our best to make this filtering exhaustive as possible by creating heuristics that deal with issues such as negation. So say, for instance, an annotation title says no alcohol found. this is not picked as relevant, despite the fact that there is the word alcohol in it, because our filtering works around the issues of negation as well. Next slide, please. So from all of our filtering heuristics, we found that among all the annotations within our documents, approximately 8.4% of the annotations were relevant for our purposes. Although this is not a balanced ratio, we work around this issue by oversampling for positive labels during our modeling. Next slide, please. So ultimately, after all of the filtering, pre-processing, this is what our final data looks like before it's fed into the Distilbert model. Our final corpus for Distilbert is the narrative text extracted from document classification, appended with narratives that come out of the forms pipeline, cleaned by named entity recognition, and then filtered by keyword search. Our positive labels for behavioral health represent presence of relevant annotations in a document. Finally, our test set is simply randomly sampled 10% of the total data set, which is used for model evaluation. So now Alex is going to take us through model performance after we input the pre-processed training data into our model and evaluate it for our test data.
Yeah, thanks, Grishma. Go to this slide. We're very proud of our results. Our narrative model yielded a really strong test accuracy at 96%, around 96%. And so, for example, I want to look you first to the picture on the right, which is our confusion matrix. So the top left corner where it says 56 is around sort of the numbers of actually not containing behavioral health documents that were classified correctly. And then the bottom right is the ones that actually did that were classified correctly. And then the bottom right and bottom left are going to be the false positives and the false negatives. I'll walk you through a few other metrics that we used. First, we have sort of precision, which is, you can see sort of on the top left. Out of all the outcomes that we predicted positive, what percentage were correct? And so in this case, it can be around sort of like, depending on which way you look at it, either 97% or 94%. And then we have sensitivity, which is also the same as recall, which is out of the actually positive labels, what percent do we predict positive? That's around 94%. And then we have specificity, which is out of actually negative labels, what percentage are predicted negative, and that's around 97%. And so these results are really good. We are very happily surprised by them. And so that sort of justifies our use of these sort of language models on classifying this text effectively, even though, we didn't have as much text data. As the work by journalists continues, we can continue to build our training and test set more and more so that sort of, it gets even more robust. And so finally, if you go next slide, we take the results from our narrative model and we take the results from the form pipeline, and we say a document contains behavioral health mention if either the forms or the narratives pipeline output true. We also want to sort of help journalists out here. So we're going to also include information like what is our confidence, which is sort of expressed by the output probabilities of the Distilbert model, or the other relevant information, which includes like what text did we use, or what did the form extract as sort of flagging under keywords, which should help journalists sort of check our predictions. And so also predict false if both the forms and narrative labels were false. And that's how we'll get the final classification for each document. And so next, just want to conclude real quick and talk about some future avenues. So right now, hopefully with our work, journalists can better prioritize which documents to look at first, which will really help the annotation process and simplify it a bunch. There's a lot of things we still can do. For example, things like more granular classification. These documents are really long. So, can we classify at the page level rather than the document level? Other things you can do is multi-label classification, which is rather than say this document just mentions behavioral health, can we say what specifically does it mention? Does it mention use of alcohol? Does it mention use of methamphetamine? Does it mention a 5150? Which would also be really useful to journalists. And then finally, hopefully we can get sort of our form analyzation on Microsoft Azure. That'll sort of really help our latency, which means it currently takes around 10 seconds to analyze a form page. And so moving our documents onto there will sort of really reduce that time. But yeah, thank you so much for listening to the presentation. We saw there's some questions in the chat that I can start answering some of them right away. The first question is when you extract just parts around the keywords, how do you know that you're not distorting the context? I guess first, we don't know actually. So if we're just extracting 5 sentences before and after, you're right. Like we actually don't know if we could be distorting the context or not. However, it's pretty unlikely based on like the size of the text that we're sort of grabbing before and after that there's going to be really necessary context, like either a paragraph or a few pages before that might distort it. But that is one possible limitation of what we're doing. And then the second one is, I believe other transformers can handle up to around 2,000 characters instead of just 500. Did you consider using one of those models? We actually did. And also it processes, just as a clarification, it processes around 512 tokens, which roughly corresponds to 512 words, not exactly. Yeah, so there's a super popular model that we tried out called Longformer. Longformer is famous because it can do long document classification. It can go up to 10,000 tokens at a time, but we tried it on our data set and it was a lot worse accuracy than we had. Part of the reason is that, the attention mechanism is really powerful. And so rather than scaling either quadratically or exponentially with the size of the input text that we have with the Dilbert, it's just linear for Longformer. And so that's some of the reason it might not perform as well on just a general sequence. And then for using many
Alex?
segment, oh yeah.
Before you move on to the next question, I think some of your teammates want to chime in too. Specifically, Amanda, I think you had indicated wanting to answer one of the questions. Is that correct?
Oh, no, I'm just answering them from the back end so that they appear in the chat, hopefully.
Got it. Okay. In that case, if no one else on the team wants to address one of the first 2 questions, then we can definitely move on. Go ahead.
Of course. And then for the segment embeddings to learn a document level embedding, one of the reasons we didn't do that is because different jurisdictions sort of have such different formats for these documents. So we can't really include like a position embedding very well because one jurisdiction might have a completely different way of reporting one of these police records. And so we can't really learn based on like the position of the text, where to find important information. And so I'll pass it off for my other team members to talk about the other questions.
Just to tack on.
Oh, go on. Go on.
For the document embeddings, one other reason is that when the documents are like tens or hundreds of pages long, oftentimes it happens that the words we're interested in, the keywords, only appear a few times across a few pages. And we tried a few different techniques of learning document embeddings actually, but they just don't end up representing the keywords we're interested in very well, just because they appear so infrequently. Yeah, sorry, Rishma, go on.
Thanks, Salil. So to answer the question, how did you assess the accuracy of PyTesseract? So initially, our plan was to use Azure Computer Vision instead of PyTesseract because using it in a couple of documents, we found that Azure Computer Vision works better, but due to I guess, computing issues, ultimately we had to pick PyTesseract. And in terms of like checking for accuracy, the thing we've mostly done is done manual checking. So looking at a couple of documents and seeing if it has extracted text like the way we wanted to. And so far the results look pretty good. So I hope that answers your question about that. And the second question, could you use your masking techniques for redaction purposes as well? So named entity recognition package inherently doesn't have a redaction function, but we can definitely write a couple of codes to mask or redact those names. And that's what we've done for our corpus as well. So it's definitely possible. Yep. So did you have a quality check to measure how accurate your labeling method was? Yes, we've done it, but like I said, it's mostly not computational, and we've like picked 20 to 30 documents and tried to check them manually, and they look good. I hope that answers all your questions.
Well, certainly we have exhausted the queue at this point. So thanks, team, for answering all the questions. But I think now the floor is open for further questions. So both teams are online. And I want to really first thank them for the hard work they've done over the 8 weeks. It's as a person watching them do it, it's been amazing to see them go at it. So let's give the attendees a little bit more time to see if they have other questions. Please feel free to type it into the Q&A, or maybe you can, I don't know whether you can raise a hand or not. You could do that as well. All right, I don't see any questions. Well, if there are no further questions, I guess we are done. And thanks to everybody for attending. And again,
we have a hand up.
And Shilan, so you had a few things to say or something?
No, Mia had her hand up.
Oh, sorry.
I sorry, I don't have any further questions. I just have great jobs, both teams. I just have a quick comment regarding the COVID mortality team's project. I think I really appreciate that you're doing county level analyses, because we just had a discussion with Dr. Sarah Cody, who is the health officer of Santa Clara County. Apparently, like even adjacent counties, the policies are quite different. San Francisco County and Santa Clara County are always on the same page, but we have San Mateo County in between, who is always like not on the same page with us. So it's driving like small business and crazy. And then I'm just wondering, it could be interesting to dig into your data set and maybe write like an opinion piece on these three counties. And it's kind of interesting. It's just my personal interest. And also another thing is just like, it could be interesting to look into like whether the county is a red county or is a blue county, not to make any like, causal inference or anything, just out of curiosity to compare mortality a little bit.
Thanks, Jan. Yeah, we agree. Those are a couple of things that we've definitely talked about, the political aspect. And Kevin mentioned at the end of the presentation that one of our future directions of interest is looking at this like compliance metric and trust metric. I think there's a lot that's baked into, like not just the county policy, but also how people feel about following county level policies as well. So I agree, county level data is so interesting. We've had a really good time this summer, I think, looking at all of the different county level features and trying to understand just what's going on at the county level across the US. Yeah.
We also have a hand raised by John Chambers. John, go ahead.
First of all, just congratulations, terrific congratulations to both the teams. And one suggestion, which I'm sure you've thought of already, for the journalism thing. As you know, there's the Brown Institute for Data Journalism and related things, both here at Stanford and in Columbia. And I'm sure you know lots about them, but I just know because I'm a personal friend of the director of the Columbia version of that, they would just be absolutely entranced to have a discussion with you on what you've done and its broader implications for data journalism in general.
Thank you,
Thanks
John.
for sharing that. We'll definitely look into that. That seems really cool.
And we have also a hand up by Cheryl. So Cheryl, please go ahead.
Yeah, hi, it's Cheryl Phillips. I just wanted to add to what John just said, and that is that, so Big Local News actually is a recipient of grant money from the Brown Institute and have been a recipient for several years now. And so I'd be happy to talk with anybody about possibilities with Brown Magic grants in particular, where they fund specific projects. So anybody can just reach out to me. I'd be happy to help with that. So thanks.
Thank you so much, Cheryl. I see no further hands up and no questions in the Q&A. So I think, Naraz, you were about to give your closing speech. I think we can go back to that part.
Well, I think, again, the closing speech is really more a thanks to all of you for attending, and of course for both teams for working so hard. Actually, unfortunately, their work is still not done. They still have a few more days to go. They're wrapping up, but they really are, burning the midnight oil, as they say. So I think very proud of their work. So thank you very much. And with that, I think we are done.
Thank you so much, everyone. Great job.